talker and n minus 1 plus of 1, the talker also to be the listener. Then we said the data transfer will be efficient and without any noise interference and all. Okay. So how many ways this bus can be used, or how many uh, like distributions that is possible? So something like a bus can be at a centralized point and it can be distributed equally between the destinations. Okay, if this is taken as bus, all these will be the destinations, and the moment which one want to send the data, that becomes the talker, and the remaining becomes the listeners. Okay, or what you say, the destinations. So we are not taking isolated source and destination, but this is a unified source and destination sort of thing. So the talker will be the one who is trying to send the data, and the receivers automatically becomes the listener. Okay, so this is a centralized thing where the bus will be at an location which is equally distanced placed. Or the other way is that the bus can be parallelly available to all the destinations if this is taken as bus, if these are the destinations. Okay. So it can be formulated this way. So this is bidirectional sort of thing. Here also, it's not that only it will be sending the data, it can receive the data, because what we are taking is a moment. The one which is trying to send the data will be the talker, the others will be listener. Okay, the later moment, if the point that was earlier sending the data may be in a position of receiving the data also, source and destination. So this is bidirectional moment of data through the data bus. So the same way, the destination and the data bus, here also the same concept, where one will be the talker, the other will be the listener. The others remaining will be listener. Okay, not only that, the one who talks also can be the listener, as we were seeing yesterday. So how best this bus can be controlled? We have a few methods coming over. This bus controlling can be done by using a multiplexer, or something like OR gates or buffers. Okay, what is the use of buffer?
It will
Will
that buffer is one only. It will do the function, ma'am, or else it will.
buffering means it's something like storage element. Okay? It's storing the data. Okay, so here multiplexer, we know the concept of multiplexing. So here where the sources and destinations be placed is if you take a mux based on the size or how many destinations you have. Based on the number of destinations, we try to fix how many number of inputs the mux will be having. Okay, so each device, or what you say, each destination, or a device which is trying to send the data or receive the data sort of thing, device 1, 2 and so on to device n we are taking. This becomes the selection line, where it depends on how many number of destinations, or what you say, the devices you are getting connected. So n is to 1 mux will be taking, and this is your bus. Onto this, the data will be transferred. So what is the operation is, the one which is trying to send the data through the selection process, that device will be selected, that will be sending the data onto the database. And this data will be available for all the devices. This one means that the other devices which are not selected will be by default the destinations. Not only that, the one which is sending also can be the destination, or what you say, listener. Okay, so this is what you say, a mux approach. Selects one source, or what you say, one talker, and the remaining becomes the listener or destinations. All will be destinations at a time. This is one simple approach, or what you say, simple method of controlling the bus. And maybe if isolated control of the devices we want, isolated control means independently we need to control which device to talk and which device to listen, sort of thing. Maybe listening, we can take it as all can be the listeners, as we are saying there is no restriction, but how many talks we have a restriction, only one to be talking. So maybe if this is the data what we are putting, different data we are taking on to different devices. Okay, each device will have its own selection, or what you say, enable, independent enable or selection will be taken. And this selection line, if it is enabled, okay, then only the data will be sent on to the data bus. Now here we are taking an iteration of what? Sorry. And this will be your data bus. And this data will be again available back onto your devices. You can tap them. You can have the connectivity. Either these devices are fed from different sources, or through the database itself you want to take the data also, it is possible. Okay, you can have that facility here. This is simple and or logic. This is mux logic. All well-known logics will be utilized here for controlling your bus. Then another aspect is say buffering. We are saying buffering means something like the data what gets transferred is either or a device, if it is there on a circuit, it can exist either in condition of on or off, or doesn't exist. This is one more condition we are putting in. Means that only if it is used, it will be on, else it is appearing as if it is not existing in the design. Any device can have only these three options, sort of. If a device is there, if it is say two mode device, it is on or off. But this buffers has the facility that facility in the sense, if you are using that buffer, that will contribute to the data transfer or contribute to the function. If it is not used, it will be as if it is not existing. It won't interfere into any of the circuit performance. There won't be any interference. Okay, this is what we call it as three-state buffer. Using this three-state buffer, we can control this data bus in such a way that, say, each device, as we are saying, if you are using, it will be enabled, okay, on. If you are not using, it will be disappearing from the circuit. Disappearing means it is not that physically it is being removed, but physically it will be present, but its contribution or its disturbance to the device or the circuit won't be there. Okay, So each independent buffer will have an active low signal, and the data will be sent through. So how many you are using, that many devices, that many tri-state buffers will be taken. And each device has its own, say, data input. When you are enabling that buffer, that corresponding data will be transferred onto the bus. If we put this as, say, bus. Okay. And what is the meaning of this buffering is, it's trying to store the data and you are enabling that and using that whenever you want the data to be transferred. Same way, this bus, the data that is available on the bus can be parallelly be made available to all the devices. Okay. So here we have a choice of either the data being taken from different sources or that is taken from the data bus. Okay. So something like what are the advantages and disadvantages comparatively if you take it? Say mux you can have based on the size of the mux, that many number of what you say the devices can be connected. It's a simple what you say lookup table sort of thing. What is that maximum size of the mux available in the market, that will be taken, that many number of devices can be controlled by that mux. Okay. And here the logic is that how many number of devices or this, what you say the destinations or the nodes are there, that many number of AND gates are needed. The more the devices, the more the number of AND gates, and the more the number of AND gates, the fan-in will be more. You need to increase the fan-in of the OR gate. Okay. Maybe only for simple or what you say less number of devices to be operated, maybe this can be used. Maybe this will be suitable. If more number of devices are there, maybe this becomes more clumsy and cost also. Cost effective is max. Like you can control or you can add many devices until how many number of devices it can take based on the number of n you are taking. And this buffer, tri-state buffer is used where, say, if we don't want to have any influence of any segment or any portion of the circuit in the total top level design, maybe we try to take the three-state buffer in the sense that when it is on, not used, not enabled, it won't be appearing into the circuit performance. That way of isolation, if we want, maybe this three-state buffer we need to take. But here, what is the need or how many number of buffers are needed is directly equivalent to how many number of devices through which you want to transfer the data. Number of devices is equal to the number of buffers you need to consider. And this tri-state open gate collector you take, I think this concept of wired OR you must have read, and I think DSD1 also we have seen this wired OR and wired AND logic. Sure, no? Wired AND and wired OR logic. Remember, for OR logic it will be taken as active low sort of thing, and for AND logic it will be active high, or what you say high. Logic low or logic high of your inputs defines the AND gate or OR gate in the circuit. Something like if you remember that. You remember? Say I need to implement this equation in wired AND and OR logic concept. With the use of pull-up resistor, There is no answer from any one of you. Should I take that you remember, or still you are trying to recollect? People are connected?
Trying to recollect.
Trying to recollect.
Trying to recollect. Say A and B, if I take this thing, A dot H, B dot H, if it is this through the VCC, it will be A and B, the logic what you get here. And this is active high, what we are taking. And say C is active low, I'm considering. And this has to be taken as a active low signal that will be connected to, say here, this is high, means that there is an inversion needed to make this as active low, and this is already active low. So this will be, so replicate this here, I'm taking this as active low. These two elements, if you take, or this is active low, and this you try to invert that becomes active low. So both active low, if you take through that pull-up resistor sort of thing, this becomes A, B, or C dash. Because this is low you are taking, this is low. Consider that directly. If it is high, what say if it is C dash itself, C itself, if this is dot H, we need to take the inversion of this, and that becomes low, that will be connected. So that will be, say, if this is the connectivity, it will be AB or C. See, what is this we are taking is this element will be AND gate, because these are active high signals and active high out. And this, if you consider this one, this portion will be OR gate. This will be OR gate. This can be implemented using your open collector transistors. Transistors with open collector, maybe in basic electronics, that is a topic there. What is open collector? Okay. So this is open collector or open collector gate. Open collector gate. This is also a sort of buffer aspect only, wherein, see here, we need to take the devices with an AND logic, and the one which is to be talker will be enabled, and the others will be uh, idle. Idle in the sense they won't send the data. Maybe they'll be in the receiving end, but not sending it. Okay. So here, this open collector devices, if we take, maybe OR logic if you need to implement, because why we take OR logic is only one will be taken for what you say, sending the data. So why OR logic is with low voltage, as we have said here, it should be through low voltages. OR logic if you need to implement. So any device you take, I can use a buffer in order to make, say, if this is dot H, A dot H, if it is there. I need to get this as an OR gate. It means I have to make this as an dot L. Make a buffer, use a buffer to make it as a dot L. Now this is now ready to be taken as an OR logic. This one, OR logic. Okay, say B is dot L, say. That means already it is low. Either you can take a buffer of this sort, okay, or that means logic low only, buffer only this is, or else directly you can take this as an active, B dot L. Both two options you have. Ultimately, when I need to put this as say A or B, implement this as A or B, I need to take these outputs to be low voltage. That is what we are implementing. Either this format you can take, this format you can. Okay, so how many devices you have, that many buffers will be taken based on what is the logic that is available on that, and it will be ready or made ready to be available as the logic low, or what you say, low voltage available, okay, through the pull-up resistor. If you take this, becomes an OR logic implemented. So this transfers the data, which device you are enabling. Through that device, the data will be coming. Okay, can you put AND logic? Can you put AND logic for this data transfer?
No, ma'am.
No. Why? Because OR is any one of the input is true, output is true. But AND logic, all inputs has to be true. But for us, only one talker should be there. If you take AND logic, all will be talkers. Then only output will be sent on to the bus. So only open collector or configuration, or something like wired or logic element will be used. So four different bus controlling approaches are there.
Ma'am,
Depending, yeah.
why do we invert the voltage, ma'am, in a open collector gate one from high to low?
High to low means for OR logic. OR logic, what is the logic needed to be presented? The input is logic low. Na?
Yes, ma'am.
This is dot L, this becomes dot A. Dot H becomes dot L. This fellow, though you are making this here as a bubble, it means that here it is low. Na?
Yes, ma'am.
So the point of input where you are taking it as a wired OR element, it should be low. That's the need why we are taking this as active low. Okay.
Yes, ma'am.
Actually, this device is a buffer device where you can use this as conversion of voltage level or directly transferring the potential as it is. If low is there, maybe some, check out what is this IC, buffer IC 74LS22. 22, not 22, 44, I suppose. Check this in your IC list. Okay. So one of the output or something like when we are using the device, that will be enabling, or through that buffer, the data will be sent on to the data bus. Normally, these are also called as buffers only. Okay, because those are the data transferring elements. Okay, but what are like the points of consideration for deciding which control or which type of bus controlling technique to be used is, it depends on how many number of devices you have, okay, and how much of the cost element that you can have in your design. All that parameters comes into consideration. So this is something all related to our design aspects, design considerations. for one pressure applied on the button. Let it be any duration, how much time the pressure is applied, only one pulse has to be coming out. Okay, only one pulse has to be coming out. Okay, so wait till that pressure is released in order to make the second iteration, or in order to go to the next iteration. Release the button, then only for a new pressure applied or new iteration of applying the pressure on the button, it will be the second pulse coming out or the next pulse coming out. Okay, so for a pressure applied, it should be only one single pulse. Any question? Someone has unmuted. Okay. So what we are saying is this button signal is not synchronous. It is not happening at some what you say frequent intervals or equal intervals sort of thing. Anytime it can happen. Normally in our ASMs, an star or asterisk onto the top of the signal will be indicating the asynchronous function or asynchronous aspect. Say, if I take this as button, B is the identification or name given to that button, and star on this indicates that this is asynchronous. Normally, whenever there is an asynchronous element or event happening or a signal happening in the design, we need to send this, or we need to make this synchronous by applying this signal or sending that through a D flip-flop. Then this becomes a synchronous element with the system clock. This is our known remedy, what we are using for every asynchronous input. Okay, even in the design guidelines, we have seen this point. Wherever there is any asynchronous event or signal happening, try to run that through the D flip-flop so that it gets synchronized with the total overall system clock. Okay. So now here, taking the control algorithm, something like we are taking the aspect of architectures versus the control algorithm, no? And this gives us the status which issues the signal. So now we try to design this control algorithm, and this control algorithm is something like we make use of this asynchronous signal that's happening. It's sent to a D flip-flop. Maybe we let us name this as the button status which is synchronized. I name this as D sync. We try to see what is this signal condition, whether it is pushed in or released, whether this button position is put in or released, issues us to outputs. Okay, whenever it is pushed in, we should initiate pulse, and that pulse should be hold until we get a release signal for that iteration. Okay, so that is our algorithm. Now I put this as something like searching is one state I would like to take. I'm searching for the status of the button, and another state I take is hold that pulse. See, what is that we are doing is first search for the status of button. When the button is pressed in, we need to give a pulse. That pulse will be hold until it is released. That is the complete logic. So I try to take this as a two-state thing. I name one state as search. What is that search I'll be doing is I try to take the synchronized button signal as the test condition. Okay, and if this is not pressed, means that it is false. If this is not pressed, this is false, it will be still searching. Okay, and say if there is a manual initiation of button pressed, then it has to give us a conditional output, which is pulse. Okay, maybe single pulse, make this a single. Give a single pulse as the output. Okay, now how much duration this should be on? What we have done, first it is off, pulse is not there. Once we have seen the button pressed, we have issued the pulse, but what duration it should be on will be again decided by the condition of the same signal, this one, whether that button is released or not. Okay, now here, after you make the pulse signal 0 to 1, what is that we need to do is hold that and try to see what is the status of that output, this sync. If this is false, if this is true, true means still it is not released, it will be holding that. That means this will be holding in the same position. If it is released, means that it has to reset. Means reset means I'll take this back here, release it, and search for the new iteration. Search for the new iteration. Is this understood? A simple logic of generating a single pulse for an iteration of what is that button position being pressed or released. You are generating a pulse. So that pulse will be only one single pulse for one press operation. Okay. So how many number of state variables are needed here? How many test variables we are having and how many state variables are needed? State variables are ABs, whatever we are indicating here. Two states you have, so one state variable is enough. Is that correct?
Yes, ma'am.
Two states. So one state variable may A be, A is 0 is search. If you take A is 1, you can take it as hold. Okay, and one test variable, that is B sync. Okay, and one output, that is pulse output. Okay, and this thing, maybe here if you take the test variable you are taking in search and hold operation is variable or different. The button sync test variable, this is variable we are taking. Is that the same test variable we are testing here in the hold position?
Yes, ma'am.
That means maybe I can make this as a single state thing also, because maybe if I put this operation into a what you say another D flip flop, okay, something like B sync, I'm taking this into another D flip flop because this is coming from one D flip flop, this is coming from another D flip flop. I take this as delayed. Okay, delayed means the same signal I'm taking at a delayed stage, at the later stage. Okay, how much duration this is? The same thing I'll be having here until the same what you say in the clock. Now, if I take in comparison operation, if this is released, See here, if this is released, this happens at earlier position than this delayed version. No? The operation of this button, what happens at D1 and D2, if you take D1 output happens at the earlier stage than D2. No? That means if there is a release in this button, this goes opposite value and this will be still the old value. Then your equivalence operation will be different. No? This is different from this. That won't be equal. Until that this output is equal, you put the pulse on. You put the pulse on until these two are equal. Then I can even cut down the number of states. Something like this. I'll draw here. I'm taking a such a state, and this such a state I'm taking the sync. That means first D flip-flop output. If this is false, I'll wait for searching. If this is true, I'll see whether these two values are same or not. The second output, delayed output, I'll see. And if this is what you say, true and false, if I take this way, this is true and this is false. See here, if both are true, that means what I'm getting here is if I try to release or what you say, issue the single pulse or else try to reset back. This is the iteration you get. Means that we are trying to assess whether they are similar or different. Okay. If they are having different things, issue the pulse, reset back. This completes in one state. This is one alternate, like how to refine your ASM. I'm defining this. Okay, come back here. How to design this? Let me complete. Designing this total ASM. Now we need to define the equations. How many equations are needed here? How many equations are needed? Your search operation is done when A dash. Hold operation will be done in A. Okay, so I can relate this. Now search is equal to hold bar, or hold is equal to search bar. Both means the same. One is complement to the other. One is complement to the other. Okay, so I can take this format now. Let me remove this. Okay, what will be my circuit which implements this total logic is, first will be the button signal, that is push button thing, which will be taken through a D flip-flop because this is asynchronous. We are using a clock to make this to be synchronized. Now this gives us this synchronized button put, and this output along with how much duration we are testing for. I'll take this through other flip-flop and say this will be our search operation and this will be the hold operation. This gives you the hold output. Okay, and this hold I can take something like this. I can take a combination of mutual search of these two and which releases me the single pulse, because these are the signals on which the pulse duration is dependent. These are the, that means same signal. So that's why we are taking that through what is the duration for which it is hold. And this clock should be same system clock. This is very simplest of simplest design. Okay, understood? Any doubts? Okay. So far we said a clock used in the design, that is system clock you are saying. How to design that clock itself, let us see. Normally whenever we take this system clock, that is through another circuit actually. Loosely we are saying, say some through flip-flop we are taking this clock and all, but there should be some source of a circuitry which generates the system clock. That means this is operated based on an oscillatory circuit wherein it is something like divide by 2 operation will be done. So based on what is the frequency of this oscillator, by 2 will be the clock generated output. Okay, something like this. Say if this oscillatory frequency is this is the frequency of the oscillator. Okay, our clock, the system clock, the output of this is what we are naming as system clock. The system clock output will be by 2 we are saying. So this will maintain 1-for-1 oscillation, complete oscillation, and it resets and goes to 0 for until one more oscillation. That means one cycle of oscillation. So this will be your clock. This is clock. So can I take this as divide by 2? Divide by 2 operation. Say I want 20 nanosecond clock signal. Means that
move the screen up.
Huh?
Can you move the screen up?
What happened?
Can you move the screen up? The diagram.
Which one?
This presentation.
I couldn't get you. Moving?
No, I can't see the upper part. Can you move it down like that?
Oh. No. We are just like, this is the design till this only. That is the previous design. Okay, let me do it fresh then. Okay, your system clock. So if this is your oscillation, frequency of oscillation, if this is your oscillator, your clock will be this one. Means that say something like 20 nanoseconds of clock is needed. This should be 40 nanoseconds. For every 40 nanoseconds, you will be getting 20 nanoseconds. That means 20 nanoseconds it will be something like what you say, frequency should be double that. Yes or no? You are getting one cycle in this total 20 nanoseconds. It is total clock means they should be 10. They should be 10, na? 10 on, 10 off. So how much should be the speed here now? This is for total of 10 plus 10 plus 10 plus 10. That means 20 plus of 20. That is 40 it should be. This divide by 2 sort of thing we are seeing. So your oscillatory frequency decides the frequency of the clock. Oscillatory frequency decides the frequency of the clock. Now, this is an automatic generating system clock. The same system clock in the same design, you can operate that manually also. Manually, you can generate different pulsed clocks. That means it's like if it is automated, it will be equal on-off duration. Okay, if you want say 50%, this is 50% duty cycle. We say 20% duty cycle, 30% duty cycle, or 60% duty cycle sort of signals also you can generate. That means that I need to switch on for some duration and off for more duration. I can generate this type of clock, or I need to have more on time and less off time. This is unequal. This type of signals can be generated by manual operation. So your the device, what you are saying, the device or the source of your clock should be having two modes, something like manual mode or auto mode. Auto mode depends on the oscillatory function. Manual mode, something like based on the button operation, we will be fixing this manual mode. Okay, this generates what is called the clock signal, which we try to give that to the circuit, any circuit. Okay, so here, if you see something like this, if your design is in auto mode, it even if it sensitizes any manual interruption of the button, it should not truncate the auto mode in between. It should complete one full iteration. Okay, and whenever there is a release of the manual operation, it should automatically switch over to the auto mode. These two things happen. Whenever your source is in auto mode, it should not truncate the auto mode operation if some manual operation is initiated. Once the manual operation is complete, it should go to auto mode by default. These are the two conditions what we are putting in now. Okay, so something like, what is the test condition and what are the outputs we have for this design? What is the test condition and what are the outputs? I said two modes of operation, auto mode and manual mode it has. Auto mode, we don't need to have any further testing because it needs to complete that complete iteration of on off of that clock. Okay, but once if it is not auto mode, it will be manual mode, or vice versa. If it is not manual, it will be auto, vice versa we are taking. But if it is in manual mode, there should be an iteration, or what you say, a test condition based on the button position. If button is switched or pressed, it should be initiating the pulse. If it is released, it should be switching off the pulse. These two has to be the outputs now. That means here in the manual mode, one more test condition is coming. That means first test is whether your design is in working in auto mode or manual mode is first test condition. The second condition is in manual mode, what is the position of the button? Understood? I'm moving the screen up. Hope you have drawn that. Okay, now if you understood this, let me take, say, how many outputs are there? How many outputs we expect? Because this is a clock function. This is clock function. Outputs are two on, sorry, this is 0 or this is 1. That means I can take this as off or on. Two conditions. Okay, so this will be having two states. Two states. One is I'm taking it as off state. Okay. And this is off. What will be the output of the clock? I'm saying as taking this as system clock. Will be 0. Off means 0. Now here the priority signal is, we are taking manual as priority signal. If manual is false means it will be auto mode. Okay, that condition I am taking here. So I take this as manual. Okay, if this is manual operation, true or false. If this is false means this is auto mode. Okay, if this is false means what happens is, your by default you are going to a state of on, because this is auto mode based on your oscillatory signal, and here the system clock will be 1. Okay, if manual mode is true, what we need to see is what is the button position. This one, I'm taking this as button position. If this is released, I name it as false. If B is released false, B is pressed, it is true, I am taking. Okay, if B is false means it is released, it will be low, clock will not be initiated. Okay, if this B is pushed in, pressed, then it will go to a state of on. Okay, in this state, again what will be done is, this is my next iteration. In this state, again the condition of whether it is, say if it is in your manual or auto mode, your clock is made 1. How much duration your clock has to be 1 will be again decided by whether the iteration of your the condition of your manual is true or false. If this is something like, say, false, means that it is auto mode. If it is in auto mode, it will directly reset back to off. If this is true, means that this is in manual mode. Again, check for the position of the button. If that button is released or not. If it is not released, that means it is true. Still it is pressed. Clock should be 1. If it is released, then this should be reset. So this goes here. is false. Able to catch the logic here now? You have two states of clock being 0 or clock being 1. The switching between on off of the clock depends on the manual operation or auto operation of the clock. Okay, so manual operation is taken as the direct test variable. If manual is false, means it is auto mode. Auto mode by default, based on the oscillatory frequency, it will be toggling between clock is 0 and 1. Okay. If it is manual mode, we'll be checking the position of whether the manual button is pressed or released. If the button is released, it will be resetting the clock. If it is pressed, it will be initiating the clock. Okay, how much duration it will be initiated will be again checked for the button position. Okay, if it was in auto mode, directly after that oscillatory frequency, it will reset this part. If it is in manual mode, what happens is this will be checking for the releasing of the manual button. If it is released, it will be resetting the system. Okay, try to understand this ASM. Maybe next hour we try to continue this design. Hope the transitions are clear now.
Means second manual, when it is true, can we attach it directly to earlier button?
Manual in the second
When,
manual testing.
when it is true, can we attach directly to earlier button?
No. If it is true means it is in manual mode. We try to check whether it is released or still pressed.
Yeah, earlier button also we have same conditions, so can we directly attach it to that button?
No. See, first iteration is that checking for the position of the button. Okay. Once it is true, we need to generate one another function. No, clock has to be set. After setting the clock, again you have to test the like position of the button. Because see here, when this is true means that if you direct this back here, what happens? You are truncating that, like iteration of that auto path will be truncated. No, actually, this auto path decides or will be decided by your oscillatory frequency. If you take it back, what happens is it will again truncate that initialized auto mode, and it will be taken to a new clock to be one. No? Actually, these two iterations are cross verifying whether that pushed button is released or not. You can do some condensing of the map. Okay, if you take this in between path, you can condense that, and you can have this same iteration to be repeated. That means checking of the manual button position.
Ma'am, what happens if we again attach push button from manual to onwards? Like after taking from manual to onwards, again if we connect to starting button position, what will happen?
No. Question is, if you are in manual mode.
Second case, ma'am. After checking after from clock auto mode, again if we connect it to starting a button position, then what happens, ma'am? Like
I
what
couldn't get your question. If this is in this test mode, okay. If this is in manual mode, that means this path, no?
Yes, ma'am.
Uh,
If we connect it again to the previous button position.
no, it's not button position. This is test condition, na? Is the meaning of this is you are testing whether the button is still pressed or it is released. We take this format also. Maybe let me do this little bit. Okay. Because here, after taking this, so you want to take this. See here, this is off, this is on. Okay, off means your clock is 0. This will be 1. So here again you are checking back. This is a manual operation, and this is auto operation if it is false. Now, if it is true, it is button position. If button position is released, this one. If button position is true, what to be done? True, it should make this clock to be 1. Okay, and again, if you take this path, then also it will be correct.
Okay, ma'am. Now it's clear.
That was your question, no? Here, when you are taking the
Yes, ma'am.
position of B.
Instead of using another button, can't we reuse that same button position test condition again? I'm asking.
The same button position only we are testing.
Okay, ma'am.
Though I showed this as 2 different blocks sort of thing, it means the same, no?
Okay.
See, after this one, after the clock being set as 1, whether it is in auto mode or manual mode, again take the same test condition of manual or auto check. Then if it is manual mode, then check for that button position. Say something like this path if you take. Say we are initializing a button press. That means it will be this path, initializing this path. So this is still not released means it will be true, making true, and you try to remain or make this clock to be 1 until it is released. So this will be the loop until it is released. It will be true. Once the button is released, it goes to 0. This is for understanding. This is consolidated. Yes. Okay. Next hour I'll continue this. We need to take the equations and we need to take the design hardware. Okay. Try to understand this, and if any other possibility of again refining this ASM, do this and let me know in the next hour. Okay.